Hello everyone, I hope you're all doing well. So I have a nice pleasant surprise for you in the form of a problem. Okay, this is one of my favorite problems in particle kinetics. And I'm going to walk you through some of the details of the problem. I've already written out some of these things here. So I don't want to rewrite and talk about many of these things again and again. I just want to reiterate my points. All right. So I start off by having block A, okay, which is lying on this incline here. The mass of block A is given to me, so I'm just going to put a small tick mark right next to things that I'm done talking about. Okay, so the mass of block A is given to me in this problem as 10 kilograms. Acceleration due to gravity is given to me 9.8 meters per second square, and then there is another block that is sitting, which is block B, which is a little more massive than block A. Okay, and the mass of block B is given to me as 30 kilograms. All right, what else am I told? I'm told that I have the pulley and the cable system here. Okay, so the pulley plus the cable system, these are supposed to be having negligible inertia. You see there are two pulleys. One is a fixed pulley, the other is a pulley that can move up and down, so they have negligible inertia. So I'm not worried about the motion of these pulleys as such. Okay, the cables are also supposed to be frictionless, so that's fantastic news. So here is the cable and pulley system. You're asked to treat the blocks as particles, which is even better news, and which anyway we don't have much of a choice because we don't know the dimensions of these blocks. Okay. Most importantly, I come down here and I see that, okay, for block A, I'm given the coefficient of static and kinetic friction values 0.3 and 0.18, so which means that I have to make use of friction laws. Okay, so I have to make use of the Coulomb law of friction at some point, which is I don't know, maybe bad news or good news, who knows. Okay, so what am I supposed to find? I'm supposed to establish the relationship between the acceleration of blocks A and B. That's the first thing. The second thing I need to do is I need to see, hey, does the system exhibit any motion? If it does, then why, or show why. Okay, and then the last thing that you got to see is, okay, are the blocks moving? And if they're moving indeed, then obtain what the acceleration of these blocks are. Okay, when I have to establish the relationship between the accelerations of the two blocks, I have to probably make use of some kinematics. Then when I see that if the system exhibits motion or not, then I have to make use of maybe the idea of static friction. And then once again, if they're moving, then if I have to obtain the acceleration of the two blocks, then I have to make use of our knowledge of dynamics. Okay, so this is the situation. This is a fixed incline. Incline has an angle of 30 degrees. Okay, so that's a fixed incline. It's a rough incline, as you can see. The coefficient of friction is given to us. So here is the problem, and I'm going to copy this problem because I'm going to be making use of this figure quite a bit. Okay, so I'm going to copy this, and here is what I'm going to do first. Okay, so I'm going to first look at the kinematics of the problem. Okay, so let's start the solution process. Okay, so solution. And I will first look at the kinematics of the cable, pulley system, and the blocks. Okay, so look at kinematics of the blocks plus the pulley and cable system. Okay, and so this is a big hint in many of these problems. Whenever you see a pulley and a cable system, you're going to start off by looking at the kinematics. Okay, so typically whenever you see a pulley and a cable system, look at the kinematics. I'm trying to see if I have enough space here to do anything more. I don't have much space, and then what I'm going to do is, okay, once I establish that, then I will look at idea of static friction to establish motion or not. That is what I do for part B. And then lastly, we will look at the idea of dynamics or kinetics. Okay, let me write kinetics properly, and then we will be able to obtain the acceleration of A and B. Okay, so this is the basic idea. When I'm looking at static friction, then I need to include Coulomb's law of friction. Okay, so when you look at static friction, okay, whenever you see friction, you got to use Coulomb's law of friction. Okay, so that's a must in this problem. Alright, so let me first establish the relationship between the acceleration of the two particles. Okay, so how to relate the motion of blocks A and B. Okay, what do I do here? First thing is I go back and bring out my nicely drawn figure. Okay, I want to get rid of some of these peripheral stuff here. Okay, so here is the figure, and I don't know what that creature is, but I don't like it. I'm going to get rid of that. So here is the figure. Let me set it up on a nice platform here, okay, so that it's all nice aligned and straight. Okay, so what I'm going to see is you're going to see two time snaps of this figure. Okay, this is probably the figure at some time t1. Okay, so say this is the situation. Let me write that in the blue color. So this is the blocks at some time t1. Okay, so this is how the blocks are looking. And I'm going to make an assumption here because I don't know anything else. I'm going to make an assumption. I'm going to make that assumption here. So I'm going to assume that the cables are inextensible. Okay, that's a key assumption. Okay, because I don't know anything better. So I'm going to make that assumption. Okay, then what I'm going to say is, okay, hey, this same block system, I'm going to draw it at a different point in time when the motion I think is taking place. I'm going to assume that the block B, because it looks heavier to me, is going to move down and block A is going to slide up. Okay, so I'm going to take the same figure and I'm going to do some adjustments to this particular figure. I'm going to copy that and paste it here. Okay, so let me bring it to the same level, but here is what you're going to be seeing now. Okay, so this block A would have moved a little more, so I'm going to reduce the length of this cable here, and I'm going to bring out my block A, and then I'm going to bring it here. Okay, that looks good, which means that in the meantime this block B must have moved down a little bit, right? Which means that, you know, I'm going to take probably here is how I'm going to do it. So I'm going to cut this off here. This is going to be a cool trick, you'll see. Okay, and I'm going to take this guy, and I guess not completely yet. I have to just take only those two guys. No, I'm still getting this pesky fellow here, so I'm going to remove that. I'm going to take this and then slide that creature down. Okay, and then I'm going to bring this back. Okay, join it on here and join this back on here. Okay, and I'm going to take this and then bring this back on there. Okay, hopefully that does everything okay. Probably got to adjust it a little more. All right, so this looks better. Okay, so this pulley was originally here, as you can see, right? The pulley is now moved down, and the block B has also moved down a little bit. Okay, so which means that these blocks are getting displaced, and this I'm going to say is the situation of the block at some time t2. Okay, so, and I'm going to write that down here, so I'm going to copy that and write that down here. So this is the situation at some time t2, and let me tell you my rationale behind what I'm doing here. Okay, and so I am assuming, so between time t1 and t2, I am assuming that the blocks have moved and that B moves down so that A moves up the incline. Is this correct? I don't know. I mean, who knows? Who the hell knows, right? But I'm going to start off by doing something. All right, and then what I'm going to do is this. Okay, so I'm going to start measuring the length of some of these things, starting from the center of this pulley system here. So I'm going to say that, okay, at time t1, the distance of the block A, you can see this here. So I'm going to draw some of these things. Let me do that here. Okay, so these are going to be using dotted lines, which is one of my new findings from Notability. Okay, so I'm going to use a dotted line there. I'm going to use a dotted line there as well. Then this is going to be another set of dotted lines. Okay, then I'm going to say, okay, the distance from here, well, the distance from here all the way to the block B, which is a constant distance. Okay, so I'm going to call that as a constant K1. Okay, so this distance I'm going to call as K1, and you'll see me marking this distance very soon. Okay, so first of all, I'm just marking all these distances, some of them constant, some of them not necessarily constants, as you can see. So this distance I'm going to call as XA, because I'm saying this is the motion of the block along the incline. Okay, and so I'm going to just say that the motion along the incline is XA1, some length. Okay, then I'm going to call this constant length as a constant K1. This constant is the same constant length that you would be seeing here too. Okay, so I'm just going to bring that out and draw that here. So this is the same constant K1. Okay, then I'm going to have a couple of other lengths as well. Okay, I'm going to say that, okay, from a reference position, and for that I have to maybe scoot this guy a little more to the side here. Okay, so that they're all aligned together, so I don't want to mess around with that. Okay, so I'm going to say that, okay, from the position of block B, from where block B is standing, all the way to this fixed point here, I'm going to call this length as y suffix b, but at position 1. Okay, so this is going to be y suffix b at position 1. Okay, and so this is going to be a dotted line. I guess I don't want to duplicate that. Probably not a good idea. Let me see it. No, I did not draw two lines. Okay, that's good. All right, so this is the length y suffix b. Okay, which essentially means that okay, this length here, if I can draw this length here, starting from here, okay, all the way to where the block is going to be, I can draw this length here as a certain distance. Okay, and watch this. I'm going to call this distance here, okay, which is starting from the fixed point where the other fixed pulley is, that I'm going to call as another fixed length, which let me say is some K2. Okay, and I'm going to put them in dotted lines, of course. Okay, so that's a dotted line, and that's also going to be a dotted line. Okay, so this length K2, I'm going to copy that. Okay, and I'm going to bring that down here as well, without some of these other details, probably. It's not letting me do some of the things that I want to do, but here is what I wanted to do. Okay, so this is good, and I want to get rid of this entire creature that is of no use to me yet. Okay, so K1 is a constant, K2 is also a constant, keep that in mind. Okay, and then you can obviously see that the distance between the two pulleys initially is going to be a distance. If the total length is YB, then all I have to do is, okay, what is the distance here is YB1 minus K1 minus K2. Okay, so this length can be found out. I'm going to squeeze that length in here. So this is going to be YB1 minus K1 minus K2, where K1 and K2 are constants. And I'm going to do something similar here as well. When I come back to this figure here, I'm going to say, okay, here is block B. okay, of course straight line, and then all the way from block B to where this top portion, which is also a fixed point, is sitting. I'm going to call that as a distance YB2. Okay, this is YB2. Okay, this is the Y position of the block at time 2, and of course starting from here where the pulley is sitting all the way to where the block A is, there is another length that I'm going to call as XA2, okay, because that belongs to block A. Okay, so once again these are all dotted lines. Okay, bear with me please, because this is the most important figure in this problem. Once you're done with this, then this problem is a piece of cake. Okay, so this is going to be XA2. Why is it 2? Because it's a time 2. YB2, why is it 2? Because it's a time 2. Okay, which means that I can write out this length here, which is known to me now. Okay, let me put that in dotted lines as well, and then we will be finally done with it. Okay, so this I'm going to write as YB2 minus K1 minus K2. Okay, and I'm using a couple of assumptions here. What are my assumptions? One is that the cables are inextensible. That's one assumption. And I'm also assuming that the curved length, as you can see, I'm going to darken that here. This curved length, I'm going to assume, and this curved length here of that cable along the pulley, I'm going to assume it to be very, very small. Okay, I don't want to destroy my figure, but I just wanted to mark it and show you. Okay, so that's another thing that I'm going to assume is that, so assume cables to be inextensible, which we have already written down. Okay, and also assume the wound length of the cable around the pulley to be negligible, which means this essentially means that the pulleys are being treated as a particle. Okay, so it is similar to treating the pulley as a particle. All right, so this is what we have going on so far. Okay, and those are the assumptions that we have had. Now what am I going to do? What I'm going to do is the following. I'm going to say, okay, if at time t1 I have a certain cable length, then at time t2 the length of the cable should be the same, because the cables are inextensible, right? It does not make a difference to me. Okay, so because cable is inextensible, I'm going to say that the length of the cable at time t1 is equal to the, let me not put any, is equal to the length of the cable at time t2. Okay, this is great news, isn't it? Okay, so what I'm going to say is, okay, what is the length of the cable at time t1? I'm going to call this as length L1. Okay, now you're going to help me write this out. So I'm going to go back here, and maybe I can bring this figure down here. Okay, so I'm just going to copy that and bring that down here. So this is the length of the cable at time t1. So let me bring that guy here. So look at this length of the cable. I'm going to have this piece XA1. Okay, so that's going to be XA1. Then I'm going to have this curved piece, which I'm going to assume is very, very small, right? So I'm not going to include that. Okay, then I'm going to have this length here, starting from where the pulley is all the way to where my darkened lines are. Okay, I'm going to get rid of that, but that's one of my lengths, so that's going to be plus YB1 minus K1 minus K2. Then what else am I going to be having? I'm going to be having this wound length of the cable along the pulley, which I'm going to assume is also very negligible. And I'm going to have one more of this YB1 minus K1 minus K2. okay, and we're going to say that this k1 and k2 are constants. Okay, so k1 and k2 are constant lengths. As you can see, k1 is the distance between the fixed pulley and the fixed wall. Okay, so our k2 is a distance, so k2 is the fixed distance between the fixed wall and the fixed pulley. Okay, so obviously that's going to be a constant length, and then k1 is a fixed distance between block B and the moving pulley. Okay, I hope that makes sense. Okay, so which means that since k1 and k2 are a constant, I can then say that this length L1 is going to be xa1 plus 2 times yb1 plus some, 2 times these constant lengths, so plus some constant. Okay, plus or minus, it does not make a difference to me. Where if you want maybe to be very particular about it, if you're really particular about it, then let me write this down here. So that's going to be minus 2 times k1 plus k2. Okay, so this is the length of the cable at time t1. Okay, then I got to do the same thing at time t2. What is the length of the cable? Okay, so at time t2, I'm going to maybe just copy some of these things. So length at time t1 is here. I'm getting lazy in this using this iPad. I used to write all these things on the blackboard. At the end of the day, my fingers would be burning. But I loved writing on the blackboard. My writing was really good on the blackboard. I should tell you, one of the few things I'm proud of in my life is my writing skills on the blackboard. But unfortunately, we can't use that anymore. We're all sitting up at home. All right. So length at time t2 is what I'm going to be worried about right now. Okay. So to do this, I'm going to bring the pulley again, but at time t2. Okay, so this is the situation at time t2. So I'm going to copy that, all of it, hopefully. It says something move. I hope not. I'm not sure. I think nothing moved, but one never knows. Okay, this is at time t2, and I bring this back here. So this is at time t2. So you can once again see that the length is going to be L2, and I'm going to write that as XA2, and then I'm going to write that as 2 times YB2 minus K1 minus K2, or YB2 minus K1 minus K2, one length and then one more length, right? YB2 minus K1 minus K2, which tells me that, okay, L2 is going to be XA2 plus 2 YB2 minus 2 times K1 minus K2. Okay, so this is the length at time t2. And obviously, we have the length at time t1, which is right here. We have the length at time t2, which is right here. The cables are inextensible, so the lengths have to be the same. Okay, so because of inextensibility, of the cable, L1 is equal to L2, which tells me that XA1 plus 2 YB1 minus 2 times K1 minus plus K2. This is K1 plus K2. It does not make any difference to my life. Okay, this is equal to XA2 2 YB2 minus 2 times K1 plus K2. Okay, I'm going to get rid of these constants here. So this is going to be knocked off the park. That's going to be knocked off the park as well. And so I'm going to get something really nice here. Okay, so look at this, XA1. I'm going to bring the XA2 onto the other side, or I'm going to bring the XA2 first and then write this as XA1. Okay, this is going to be, and I'm going to take the magnitudes. Okay, I'm going to take the magnitudes. This is equal to 2 times the magnitude of yb2 minus yb1. Okay, so I'm going to rewrite this once again. Okay, so this is essentially the foundational thing that we're getting from this problem. Okay, so I'm equating the magnitudes here, so please note these are magnitudes. Magnitude. But what do you know? You know this xa2 minus xa1, yb2 minus yb1, what are they called? You know, they are nothing but the displacement of the blocks. Okay, but xa2 minus xa1, maybe let me write this down separately underneath all of these. Okay, so this is essentially what I have so far. Okay, so this is a main key result that I have so far, but xa2 minus xa1 is nothing but the displacement of the blocks A between time t1 and t2, and likewise yb2 minus yb1, I'm sorry, this is yb2 minus yb1. This is the same thing. You know, I'm just going to copy this and then say that this is the displacement of the block B, you know, as I'm going from time t1 to time t2. Okay, and so which means that, you know, I can just call this as delta xa and then delta yb. Okay, so this essentially tells me that, you know, magnitude of delta xa is equal to the magnitude of delta yb multiplied by a factor of 2. Okay, and so I'm just going to call this as delta xa. So delta xa is the displacement of block A, delta yb is the displacement of block B. Then here is what I'm going to start doing, and you see that these displacements are changing with time, right? Which means that now I start differentiating it. Okay, so now differentiate. So the first relationship that I have is delta xa is equal to 2 times delta yb, magnitude only. Okay, then I'm going to start differentiating it. With time, because you see these are displacements that are changing with time, right? So essentially I can say that this is a function of time, this is also a function of time, which means that I can say, okay, d by dt of delta xa is equal to 2 times d by dt delta yb. But what is the rate of change of displacement? That is nothing but velocity, which essentially tells me that the velocity of A is equal to twice the velocity of B. I'm sorry, I'm completely losing my mind here. Velocity of B. Right? Does this? I hope this is making sense to everybody. Okay, so this is like a key relationship. So the first thing is, you know, I was able to equate the magnitudes of the displacements. Now I'm relating the magnitudes of the velocities as well. Okay, so these are still magnitudes. I'm not looking at any direction yet. And then lastly, I can say, okay, differentiate the velocity to get the accelerations. Differentiate once more with time. What am I going to get? I'm going to get d by dt of va of t is equal to 2 times d by dt vb of t, but rate of change of velocity is nothing but acceleration, right? So this essentially tells me that the acceleration of A is twice the acceleration of B, and this is once again magnitude. Okay, and so this is the key result that we were supposed to get in the problem, and so we can finally say that, okay, so we say now acceleration of block A is twice that of block B, twice that of B. This is only from the magnitude, that's the first thing. And the second thing, I'm assuming that block B travels down vertically and block A moves up the incline. Alright, we finally got done with like maybe one part of this problem. Okay, and we got a few more things to do now. Okay, so what are the things that we need to do? Alright, so the first thing is we were able to find out the relationship between the accelerations. The second thing is, okay, are these things even actually moving? Am I doing this just for the heck of it? Or, am I doing an actual dynamics problem? So how to do that? Okay, so to see. Okay, so the next step that we need to see is, okay, I don't know if this is Roman numeral 1 or 2. So let me start off by saying, okay, this is Roman numeral 1, where we are looking at, I guess I should have written this as Roman numeral 1. Okay, so this is 1. Then I'm going to go back to 2. Okay, so this is now Roman numeral 2. Are the blocks moving? What is my strategy? Is the following. Okay, I first assume static equilibrium. Okay, then by balance of forces obtain. You see, if I go back very quickly to one of the figures that I have here, right, you see that the block that is in contact with the ground is the block A, which means that, I have to calculate the force of friction between the block A and the incline. Okay, so obtain the force of friction between A and incline, and then check to see, and maybe you can call this as F mu A. Okay, check to see if F mu A is greater than F mu max. Okay, and if it is indeed greater, then we know that motion is taking place, and so we reduce the value of F mu A to be lesser than the maximum allowable value. And if we find out that if this is not the case, then there is no motion taking place, we don't have a problem, we just go home smiling all the way. Alright, okay, so that's what I'm going to be doing. So which means that I'm going to be drawing. So this is my strategy. Okay, this is how I think about these problems, and I would appreciate maybe a similar thought process if you can come up with it. Okay, it's a good idea for these kinds of problems at least. Okay, so I'm going to draw the free body diagram. So draw the free body diagram of A and B. Okay, so let me do that here. So for that, let me go back and bring my picture up. Okay, I keep bringing these guys again and again, so that's a good thing, I think. Okay, so let me copy this entire thing here. Okay, and then let me bring it down here so that we know what we are drawing. Okay, so free body diagram of these blocks. Okay, how to draw their free body diagram. Fairly straightforward, right? So essentially what I'm going to be doing is I'm going to be cutting off the cable here. I'm going to be cutting off this entire setup here if necessary. These pulleys are massless, so that's essentially what I'm going to be doing. Okay, so free body diagram of A. So I'm going to take block A and paste that here. Okay, so this is block A. Then I'm going to be taking this entire setup here, which I'm going to cut off, and then that's going to be giving me the free body diagram of block B. Okay, so I'm going to copy that and paste that here. Okay, so you will also see that there is a little bit of the cable that will be sticking out from the end of block A, so I need to put that piece as well. So I should have probably taken that too. Okay, and I'm going to paste that down here. So all right, so if I do the free body diagram, the first thing I understand is, okay, what are the forces? So there is the cable tension. This is the cable tension, which I'm going to call as tension T. Okay, then what other forces do I have? I have a force which is normal to the surface of this block, which is going to be the normal force of reaction. Okay, so this I'm going to call as NA. Excuse me. Then I'm going to have the weight of this block, which is acting vertically down. Okay, so this is going to be the weight of block A. Okay, and of course the weight, I can break it into its components, depending on the direction of the incline and so on, which I'm going to do in a minute. Okay, then I'm going to have a friction force. I'm assuming that the block B is moving down, or it's planning to move down, which means that the force of friction is going to be pointing in this direction between the block A and the ground. So this I'm going to call as F mu A. Okay, and this weight creature here, I'm going to break that down into a component vertically and horizontally. Okay, so that or along the incline and perpendicular to the incline. So here is what I'm doing further. Okay, so here is the direction of the incline. Okay, so here is the incline, and I'm saying, okay, this angle here is 30 degrees. Okay, so I'm taking this weight and then breaking it up into a component that is parallel to the incline, and a component that is perpendicular to the incline. And you can make use of basic trigonometry to find out what these things are. So this angle will end up being an angle of theta as well. Okay, so this was the original weight, WA, and so this is going to be WA times cosine theta and WA times sine theta. Okay, and I don't want to crowd this thing too much, so let me pull that here. So this is WA cos theta, WA sine theta. And then I go back to block B, and then I see, okay, hey, this is the same cable, right? Which means that its tension has to be the same here. And then the other thing is a no-brainer. This is going to be the weight of block B, which is just going to be acting vertically down. Okay, there is nothing to think about it. Weight is equal to mass times acceleration due to gravity. Okay, so this is the free body diagram of block B. Okay, this is the FBD of block A. Okay, this is very important that we mark all these free body diagrams and kinetic diagrams, which you're going to be drawing in a minute, of course. So this is the free body diagram of block A. This is the free body diagram of block B. And so because I'm assuming static equilibrium, I can say the following. Okay, so because I'm assuming static equilibrium, so since we assume static equilibrium, okay, and here is something further I'm going to say. Okay, for this block A, this did not come out too well. This straight line here was not that great. Okay, let me do it again. Apologies, I'm just a little picky about these straight lines because I feel like they should come out straight. Okay, so this is the free body diagram and all that. I'm going to say that the direction up the incline is positive, and direction perpendicular to the incline pointing up is the positive direction for these blocks. So I'm going to call this as an x coordinate and a y coordinate, and this is a positive coordinate. This is just for block A. Okay, and I'm going to say, okay, for block B, my coordinate frame is going to be x and y. Okay, so an important thing that you're seeing here is that I can choose different coordinate frames for different particles. Okay, so for particle, so we assume static equilibrium. We know that there is no motion yet, and then I assume suitable coordinate frame for A and B, as you can see. Okay, and I'm going to bring the free body diagram of this block A. Okay, and I'm going to start summing forces along the incline and perpendicular to the incline. So if this is the free body diagram of block A, then I can say that, okay, sum of all the forces due to static equilibrium, sum of all the forces along the incline is equal to 0, which essentially tells me the following. What are the forces along the incline? Okay, this is going to be the tension T. Okay, then I'm going to have minus F mu A, and I'm also going to have WA sine theta, that's equal to 0. Okay, and then what else am I going to have? I'm going to have forces perpendicular to the incline, right? Alright, so this is going to be the force that is perpendicular to the incline. I'm going to set that equal to 0 as well, because we assume static equilibrium. And this you can easily see that I'm going to get NA minus WA cosine theta is equal to 0, where this is your theta, okay, which is 30 degrees. Okay, so once I do this, then I can find out, okay, so NA is equal to WA cosine theta, which is mass of A times acceleration due to gravity times cosine of theta. Okay, if I do the substitution, NA is going to be 30, this mass is 10, I'm sorry, so 10 times 9.8 times cosine 30. Okay, so this tells me that NA is equal to approximately 84.8 newtons. Okay, once I have NA, then I can say that, okay, the maximum friction force, F mu maximum, is equal to mu S times NA, okay, which is going to be 0.3 times NA, and so this tells me that, okay, F mu max is equal to 25.5 newtons. Okay, so this is important for me to find out. Then further, from the equation of the incline along the incline, okay, so we also know, I guess I want to write it in a black color. Okay, so we further know that from the equation along the incline, you can see that F mu A is equal to the tension T minus WA sine theta. Okay, so I'm just going to call this as equation 1. Okay, and maybe let me call this as equation 2, because I have some quantity here which I'm going to call as 1. Okay, and now I'm going to look at block B, because I don't know what the tension is, so I'm going to move on. Okay, so move on to block B, and I'm going to take the free body diagram of this block and then bring it down here. Okay, so copy that and then bring that down here. Okay, it's fairly straightforward to see that, okay, forces, I'm going to say that all the forces that are acting up, theta to be positive. Okay, so this is basic statics once again. Okay, so if you want, you can call this as Fy, and if you want, you could have called this as Fx and then Fy. Okay, it's up to you. And so from this I can essentially see that 2 times T minus WB is equal to 0, which means that the tension T is MB times G divided by a factor of 2. Okay, which means that I can actually calculate the tension. So this is going to be 30 times 9.8 by 2, or 15 times 9.8. So the tension is around 147 newtons. Okay, approximate numbers. Okay, so far so good. And so since I have the tension, I'm going to call this as equation 3. Okay, so which means that F mu A, which is equal to T minus MAG sine theta. This is equal to 147 minus MA, which is 10 times 9.8 times sine of 30. Okay, so which tells me that F mu A, if I do all the number crunching, is going to give me approximately 98 newtons. Okay, so this is 4. And so what do I have to do? Now important part is compare. Okay, what am I going to be comparing against what? I'm going to be comparing F mu A versus F mu max. Okay, and it's very obvious to see, okay, hey, from here F mu max was 25.5, F mu max was 25.5 newtons, F mu A is 98 newtons, which tells me that F mu A is greater than F mu max, which means this is a violation of Coulomb's law. Okay, which tells me that motion indeed takes place. Okay, so we have now proved that motion takes place. And if motion takes place, we now have F mu A is equal to mu K times NA. Okay, so this is a relationship which is now valid. We now have an extra equation. Okay, this is an important point. And I'm sorry that this problem is taking a long time to solve, but as you can see, it is not a straightforward one. So we have an extra equation. Okay, which means that now we are ready to do the dynamics or the kinetics of the problem. Okay, so now we go to step 3. How to obtain the acceleration of A and B. Okay, so here is what we got to be doing. Well, so let's start off by first of all drawing the free body diagram and the kinetic diagram. Okay, so the first step is to draw the FBD and the kinetic diagram of A and B. Okay, and we assume B moves down and A moves up the incline. Okay, the free body diagram is going to be the same as before, so I'm going to just bring those things again back again. So let's look at block A. Okay, the free body diagram of block A was already drawn, so I'm just going to bring that down here. Okay, so here is the free body diagram of block A. So I'm going to copy that, bring that down here. Okay, so this is the free body diagram. I need to draw the kinetic diagram as well. So how do I do that? I'm going to just maybe copy that and hope to hell that this works out well for me. I guess not. I wanted to just get rid of that guy. Alright, fantastic. Alright, and then I draw the kinetic diagram of the block A. Now in the kinetic diagram of block A, I see that, okay, the motion of block A is only up the incline. Okay, it is not going to be moving perpendicular to the incline. I'm assuming that there is no acceleration in that direction, otherwise it's going to lose contact, right? So this is going to be the following. So this is going to be mass of A. So let me write that in black color. So this is going to be the mass of A times the acceleration of A. Okay, so this is the free body diagram and the kinetic diagram. I'm going to have the same coordinate frame for both of them. Okay, so there is no change in that. So if you want, you can put that down here. So this is the free body diagram of A. This is the kinetic diagram of A. Okay, so that's what we have. And we're assuming that the block A does not travel vertically out. Okay, and then I'm going to do the same thing for block B. Okay, so what do I do for block B? I bring out the free body diagram from before. Okay, so we already did some of the hard work here. Okay, so I'm going to bring that guy down here. Okay, and then what I'm going to do further is, okay, hey, I'm going to just take this guy and then draw it up again here. Okay, I'm going to take the same coordinate frame for the kinetic diagram, draw that down here, and then I'm going to say, okay, the motion of the block is downward, so the mass times acceleration of this block, mass of B times acceleration of B, is going to be down. Okay, and so if that is the situation, then this is the kinetic diagram of block B and free body diagram of B, and then the kinetic diagram of block B. Okay, so these are the things that we have so far. The same coordinate frame is going to be held on there. Now what are the unknowns? Let me list all the unknowns. Okay, what I want to do is I want to list all the unknowns. Okay, and then I want to see, okay, how many equations do I have? Okay, if I have as many equations as I have unknowns, then I'm good to go. Okay, so look at block A. What are the unknowns? The weight is known to me, tension is not known, friction force is not known, normal force is not known. Okay, so if I look at block A, friction force of A is not known, normal force of A is not known, tension is not known. If I look at block B, and of course acceleration of block A is also not known, obviously, right? Acceleration of A is also not known. If I look at block B, what are the unknowns? I have the tension, so I have already accounted for that. Then I have the acceleration of block B, which means that I have a set of 5 unknowns. Okay, what are the equations available? This is the key step here. And once in a while I don't see why I cannot draw these straight lines. Some demons exist here probably. Alright, so from block A, how many equations do I typically have? I can say sum of forces along the incline and sum of forces perpendicular to the incline. So I'm going to have 2 force equations, 2 force balance equations. Then from block B, there is no horizontal motion of block B, so there's going to be only 1 force balance equation. Okay, then what else do I have? I'm going to bring this guy down to the next page. Okay, I'll copy that, I'll cut that, and I'm going to paste that here. So these are the list of equations that are available. Then what else do I have? The important thing is I also know that we related acceleration of A is equal to twice the acceleration of B. Magnitudes. Okay, then we also did one more thing, right? We also said that F mu A is equal to mu K times NA. So which means that I have 5 equations and 5 unknowns. Okay, so which means we have 5 equations in total, which means the number of unknowns which is 5 is equal to the number of equations. Okay, so which is also equal to 5. And so now let me start off by looking at all the equations that are available to me. I'm just going to start listing them down. Okay, all right. So it's a fairly lengthy process. As you can see, it is not trivial by any stretch of imagination solving these problems, so please make a note of that. Okay, so I'm going to start off with block A. Okay, so what are my equations from block A? I'm just going to say, okay, sum of forces, okay, in the x direction on the free body diagram is equal to sum of forces in the x direction on the kinetic diagram, and I'm going to say that okay, this is the positive x direction, positive x direction. Okay, so I'm going to start off with this equation set, which essentially tells me that okay, what are the forces? I'm going to have T minus F mu A minus WA sine theta. This is equal to MA times AA. Okay, these are the forces in the kinetic diagram. I'm going to call this as equation 1. Okay, then I'm going to have sum of forces on the y direction on the free body diagram of block A is equal to sum of forces in the y direction on the kinetic diagram of block A. Forces pointing up the incline taken to be positive. Obviously there are no forces pointing up the incline on the kinetic diagram, so the only thing I'm going to have is that NA minus WA cosine theta is equal to 0. Okay, this is 2. Alright, then I'm going to do 2 more things. Okay, so I'm going to start listing out the forces that are present for block B as well. Okay, so let me take the free body and kinetic diagram of block B and bring that creature down and then start listing that. Okay, so that's copying that. So I'm done with 2 equations, and then I'm going to have 1 more equation from here. Okay, sum of forces in the y direction for block B on its free body diagram is equal to sum of forces in the y direction for block B in its kinetic diagram. I'm sorry, this is the kinetic diagram. Important thing, look at the direction I'm saying is positive. I'm saying upwards is positive here, which means that if I write it out, it's 2t minus WB is equal to minus MB AB. Okay, important sign is this negative sign here. Okay, so make sure that you know what I'm talking about. I'm going to call this as equation 3. Okay, then what are my other 2 equations? So let me start by manipulating some of these things. Okay, so let me start doing that. So first of all, I know we also know that acceleration of A is twice the acceleration of B, which is equation 4, and then F mu A is mu K times NA, which is equation 5. Okay, so I have all these equations, and what am I going to start doing with these equations? So let me first look at equation 3. Okay, so look at equation 3. So from this equation I can say that 2 times T is equal to WB, okay, which is essentially MB times G minus MB times AB. Okay, and MB is 30 kilograms. Okay, so which essentially tells me that if I do the substitutions and if I bring the MB times AB onto the other side, so this is 2T plus 30 AB, this is equal to MB times G, which is 30 times 9.8, it's approximately 294. Okay, I'm going to call this as equation 6. Okay, and then what I'm going to do further is I'm going to look at equation 1 here. Okay, so from equation 1, so look at 1 and substitute for T from equation 6 to equation 1. Okay, so equation 1 first of all was this creature here, which I'm going to copy and bring down. Okay, so this was equation 1. Okay, if this was equation 1, then I can write the following, and I'm going to do a couple of substitutions here. Instead of F mu A, I'm going to do one more thing. Instead of F mu A, I'm going to do NA, and then I got to keep note of the fact that okay, so we note from equation 2 that NA is WA cosine theta, which is MA times G times cosine 30. And then note from equation 5 that f mu a is mu k times na, and mu k I think was 0.18 for us, so this is 0.18 times ma times g times cosine theta. So I'm going to substitute all of these along with equation 6 into equation 1. Okay, so which tells me essentially that, okay, instead of t I'm going to have 294 divided by 2. So I can make, maybe I want to do this very quickly, so I'll just divide through by t here, so that I can get rid of this t here. So I'm going to get rid of that t, and then that will be divided by 2, and then that will be divided by 2. Okay, so that's 294 divided by 2. So let me get back to my black color. So 294 divided by 2 minus 15 AB. Okay, that's what I have, minus f mu a, which is 0.18 times ma times g times cosine theta, minus wa sine theta. What is wa? Wa was also ma times g times sine theta. This is equal to ma times acceleration of a, which is twice the acceleration of b. So I'm just going to substitute that here. Okay, and what we did here was we also did the following. Okay, and I can say that this is ma times 2 acceleration of b. Okay, so which means that from above we can solve for acceleration of b. Okay, and acceleration of b, I'm going to be getting it as the following. Okay, so acceleration of b is 2.36 meters per second square, which means that acceleration of a, which is twice the acceleration of b, so acceleration of a is going to be 4.72 meters per second square. Okay, so this is the final thing that we were able to obtain. And if you want to solve for the tension in the cable, okay, so tension in the cable, if you want, you should always get this to be a positive value, right? Otherwise the cable is in it is kind of useless, right? So tension T, I can say, is 294 by 2 minus 15 times AB, or if you do the substitutions, the tension will end up being approximately 112 newtons. Okay, all right, so this is a fantastic problem, and I appreciate your patience as well in listening to me. Thank you very much, and stay safe. Bye-bye.